In this video, we're going to show how to model and analyze rocking shear walls with energy dissipative hold downs that have a flag shape load deformation response in ETABS. The load deformation response to be modeled is presented here. The designer has decided that the hold down should have a maximum capacity of 250 kilonewtons with a slip force of 125 and a maximum displacement at full expansion of 50 millimeters. The specifications of the hold downs that need to be modeled in the software are here. The initial stiffness, the stiffness before sleep, 75. The post-sleep stiffness of the hold downs, or the loading stiffness, 2.5. An unloading stiffness of 0.8. The pre-compression displacement, which will indicate the slip force. For this case, the slip force is 125, so it's minus Fs slip divided by the loading stiffness. For this case, minus 50 millimeters. The stop displacement, which is the ultimate displacement of the joint at full expansion, is 50 millimeters. Here is the model of the shear wall in ETABS. The wall is 4 meters wide and 9 meters tall. The intention is to keep the lateral drift of the wall under 1.5% of drift by putting the links. You can see two notches at the corners of the wall that are removed to make a space for the dampers. The dimension of the dampers will determine the dimension of the notches. For this case, 400 millimeters by 600 millimeters is considered for this wall. The thickness of the wall is 200 millimeters and it's a reinforced concrete shear wall. The first step is to define the link element that represents the energy dissipation devices. We're going to name the link R sub J, standing for resilient slip friction joint. The link type that we need to use is damper friction spring. This type of link element is capable of modeling a flag-shaped load deformation response. The direction that we're going to specify the properties of the link is U1, or the axial direction of the link. And we are going to use the nonlinear behavior of the link because we are modeling a geometrically nonlinear behavior for the hold downs. Here we will directly go for the nonlinear properties of the link. The initial stiffness, the loading stiffness, the unloading stiffness, the pre-compression displacement, and the stop displacement. The active direction of the link element should be both, since we are looking for the damper to work in tension and compression. The next step is to define another link to represent the foundation level. We're going to name the link the foundation. The link type we're going to use is gap. Similarly, we are looking at the U1 direction and nonlinear properties because our analysis as a whole is nonlinear. In the nonlinear properties section, the stiffness, we're going to put a large number, which in fact is the stiffness of the foundation. And we're going to leave this value as 0 because the link should not open, or in other words, the wall cannot go into the foundation at the time of the rocking. Now we're going to draw the links. The properties are SFJ. One hold down and the other one. Here we're going to set and assign the boundary condition for the bottom of the links as simply supported. Also, we're going to define a point as the shear key. So a shear key for rocking walls should be able to transfer the forces from the wall to the foundation, but should be able to uplift during the rocking motion. So we're going to free the translational degree of freedom in the Z direction. The next step is to define a joint spring for rocking toe. So the point spring property, we're going to name it the rocking toe, representing the point that the wall would bear on the foundation. And we're going to use the foundation link element that we've defined before in the plus Z direction. Here we're going to assign that point spring that we defined as the rocking toe. Now we have modeled the walls, and the next step would be defining the load cases. Before we go for the load cases, note that we have already defined a generalized displacement property representing the top displacement of the wall, like the horizontal displacement of the wall at the top, so U1 direction. The load cases that are defined, first one is the pushover loading. The load case type in use is nonlinear static, given that our links are all nonlinear, so all of our load cases should be nonlinear. Even if we are doing time history analysis, it should be nonlinear time history analysis. We are using the acceleration load vector at the UX direction. The load application is defined as displacement control here because we are looking for limiting the drift to 1.5%. So the load case will push the system at the top, so the generalized displacement that we have defined earlier is used here to 134 millimeters, corresponding to 1.5% drift at top. So we call this load case pushover loading. which shows the wall in loading. There is another nonlinear static pushover load case defined, known as pushover unloading, which unloads the wall. This load case, which again is nonlinear static, starts at the end of the pushover load case. Means that the wall will be pushed to its 1.5% drift at top and will be pushed back to its original position. Note that the direction of the acceleration vector is the opposite here. Now we run the analysis. Given that we have meshed the wall and the load cases are nonlinear, the analysis would take longer time compared to linear static load cases, and more resources are required. First, we're going to look at the deformed shape of the wall. So in the pushover loading case, we are looking at the last step of the pushover. So this is the deformed shape of the wall. As you can see, the wall went to 1.5% drift. This link, which is in tension, is fully open. And the one in compression just went down by 3.3 millimeters. This is the shear key. As you can see, it decouples the vertical movement of the wall and has moved by 23.3 millimeters upward. Defining a proper shear key is very important for rocking shear walls. Now let's have a look at the hysteresis of the joints. So in the display menu you can select quick hysteresis. That will show you the load deformation behavior of the links. This is the load deformation behavior of the link element in tension. A perfectly bilinear relationship. And this one is for the one in compression, which, as can be seen, is opened only by 3.3 millimeters. Here in the display menu, we can have a look at the static pushover curves. This is the pushover of the overall structure. As you can see, a perfectly bilinear relationship is observable here. A pushover load deformation curve or a pushover analysis is a very useful tool to determine the behavior of the structure and tune the energy dissipation devices. This is related to the loading, pushover loading load case. And this is for the unloading of the structure. So where the modeler is looking for verifying the damping ratio of the overall structure using the Jacobson's formula, the loading and unloading pushover load cases can be combined and used.